All right, so we're going to talk about today, chapter 1, starting off, and heat transfer. What is heat transfer? Heat transfer is the exchange of thermal energy due to a difference in temperature. So there has to be a difference in temperature in order for there to be heat transfer. There's a difference. You can heat a turkey in your oven, and look in there when the oven's on, and you'll see it glowing red on the coils. Or your toaster, look in there, you'll see electrical wires glowing red. Wires are hot. The toast is cool. The bread's cool. There's heat transfer occurring because there's a difference in temperature. Look in your microwave, turn it on. You say, the side walls are glowing red. Well, if they are, get out of the kitchen real fast. That's bad news. Nothing's glowing red, but there's heat, there's transfer of energy taking place. What kind of energy? Microwave energy. So there's thermal energy and there's microwave energy. We're talking in this class about thermal energy. That's a difference. Go back to thermal. You've had thermal, it's a prerequisite. This is the first law for a closed system. Equation, Q equal delta U plus W. In thermal, let's say it's a piston cylinder, you're taught how to find delta U. Give me some pressures and temperatures of air in the piston cylinder, and I'll tell you delta U. I can find it in the tables. W was called the work done during the process. In the chapter on work, they always give you a few equations on how to calculate work. The first question they ask you is the process constant pressure? Is it a polytropic process? Is there spring work being done? Is there electrical work being done? They give you equations for that. Now comes Q, heat transfer. Try and find one equation for Q in that thermal text. There isn't any. Here's what they'll say. The heat loss through the turbine, insulated turbine, is so many BTU per hour. They give you Q in thermal. Or they'll say, if this much work is done and the process goes through this temperature and pressure, how much heat transfer occurred? But they never tell you how to calculate heat transfer. That's why we have this class. This class is meant to fill in one of those blanks. How do we find that Q? Okay. So in heat transfer, we pretty much lump in the first course heat transfer into one of three modes, or three ways that heat can be transferred. Number one, it can be transferred by conduction. Number two, by a process called convection. And number three, by what we call radiation heat transfer. Chapter 1 briefly goes into these three modes of heat transfer. But then we get into depth in conduction in chapters 2, 3, 4, and 5. We get into depth in convection in chapters 6, 7, 8, and 9. And we cover radiation in chapters 12 and 13 in more depth. But chapter 1 is an introduction to those three modes of heat transfer. So we'll start with conduction. Conduction heat transfer, HT. Transfer of thermal energy from more energetic to less energetic particles due to their interaction. If I heat a steel plate on one side with some kind of a welding torch, or you can put a Bunsen burner under it, heat one side of that steel plate. The molecules in there start to vibrate. They get more energy from that heat. They vibrate, they interact with their neighbors, exchanging energy. And the energy exchange goes from the hot side of the steel plate to the cold side of the steel plate. By what? By conduction. So that's what occurs in conduction. Now, we can then look at how we calculate conduction. And to do that, we'll write down Fourier's law, the governing law. Okay, this is the basic one-dimensional form of that law. First of all, what is Q? Okay, here's what Q is. Q is called the heat rate. Heat rate. It's in watts. You can call it the heat transfer, but it's officially the heat rate. It's in watts. What does the double prime mean? It means per unit area. Q per unit area means take Q, divide it by the area in square meters, and the units then become watts per square meter. Q with no prime is watts. Q double prime, watts per square meter. The heat transfer in this case is in the x direction, so it's a one-dimensional heat transfer case. It's officially in chapter 2, three-dimensional, and we'll do that later on, but for right now in chapter 1, it's one-dimensional. So the heat transfer is in one-dimensional x. So, for instance, if this inside the wall, I'll make something up, is at 100 degrees Fahrenheit, and the hull side on the wall is 30 degrees Fahrenheit, there's going to be some heat transfer through this concrete wall from the inside here to the hull side here. which direction is it in? Hot to cold. This way. That's my x direction. X direction this way. Heat transfer occurs what direction? X direction this way. So that's what this means. Now, that K is a property of the material. In that case, concrete wall. K would be the K of that wall at what temperature? The average temperature, 100 plus 30 divided by 2. So K is a property called the thermal conductivity. It's in watts per meter K. Our textbook is all in SI, for better or worse. For you, it's for better, until you graduate, and then you say, oh my gosh, I got to convert these guys into whatever, English engineering or back to SI. So the good news is everything's in SI in this textbook, homework, examples, etc., which makes life tons easier. Okay. Where do you find K? Back of the book. Give me a fluid, or give me a substance. Okay, aluminum. Give me a temperature, 500 degrees C. Go to the back of the book. There it is, right there. Material and temperature. Now, if we look at this, let's draw a wall here. And I'm going to measure this x in this direction, and the wall thickness is L. And I'm going to assume the temperature on the left-hand side is a hot temperature, T1. The temperature on the right-hand side is a cold temperature, T2. Material has thermal conductivity, K. This is one-dimensional heat conduction. We'll discuss that in chapter 2 and 3. But for one-dimensional heat transfer, we can get rid of the ordinary differential dt dx and replace it by T2 minus T1 divided by L minus 0. That's one-dimensional heat transfer. We can just put that up here, 1D heat transfer. Turns out, for that case, the temperature profile is linear. We'll discuss that also in, I think it's chapter 3, linear. Now, let's replace the dt dx with this then. So we get Q double prime x equal minus K T2 minus T1 divided by L K T1 minus T2 divided by L K delta T over L. So that, in chapter 1, this is the important equation from Fourier's law for how we find conduction heat transfer through, for instance, a wall. Now, if you don't want the answer in double prime, let's say, no, I want Q in watts through the wall. Okay, well, what do you do to Q to get Q double prime? You multiply Q double prime by the area to get Q. So, Qx equal K A delta T over L. Area is the normal area. So if the pen is the heat flow direction, the appropriate area is the area of my hand. Here's the heat flow. Here's the area I put in. If it's this wall, and the temperature of this side is 100 degrees C, and the temperature out here is 30 degrees C, which way is the heat flow? From the hot inside to the cold outside. Heat flow goes that way. What area do I use? The height of the wall here times the length of the wall. Rectangular area, height times length. Okay, I think that's probably all we need. Oh yeah, one other thing. You say, well, oh, by the way, this law came from Professor Fourier way back, But he didn't derive it from something. He did some experimental investigations, and he found out that this was the way the heat flow seemed to respond to a change in temperature or change in length or change in material. So he derived this thing from looking at experimental results. But you might say, boy, I don't understand him. Why would he put a minus sign in front of that? I mean, that sounds ridiculous to me. He put that there, really? Professor Fourier? Well, yes, you have to. He figured it out. You have to. Here's a picture. Hot temperature, cold temperature. You know which way heat flows, from hot to cold. Q. Which way does it flow?